So the title of the talk is Practical Considerations for Canopy Management, but I'll be delving into crop load management in this talk as well. So we talked a little bit about the Grapevine Architecture of starting in the first day with Matthew Fidelibus' talk, but the canopy is essentially a shoot system of the grapevine. It's made up of the stems, the leaves, and the clusters. Collectively, this system will make the microclimate of the vine. What I mean by that, the length of the canopy, its height, its width, and the exposed leaf area interacting with the shoot density will make up the microclimate of the grapevine. So here's a handsome picture taken in Kern County. This is a Syrah canopy on a split trellis. The microclimate of this canopy is affected by the amount of leaf area, its distribution, and the interaction with the above ground climate. So we're essentially trying to manipulate these few square inches by our cultural practices. However, vineyards are very large systems. Plants are growing in communities. They're not growing individually. So, and we're worried about fruit maturity in these giant systems. So the mountains here in the back are the Tehachapi Mountains, and these rows are about 2 miles long. And we have to make a mature product here, and we can define this maturity as the point at which fruit composition most closely matches that required to make the style of wine desired. So the cultivar here in question is Pinot Gris, growing in Region 5, possibly Region 6. So manipulating these can be a challenge because we have some desirable aspects that we care about, such as uniformly ripe fruit. This fruit has to be sound, with an abundance of flavor, with correct composition, and it has to reach a peak at an ideal time, avoiding inclement weather, and of course, avoiding winery logistics, which can be, metaphysical at times. It does not make sense to me. So we looked at this figure before, the growth of the berry and its development. We have the double sigmoid growth of the berry, where we try to, accumulate compounds post-veraison that might be beneficial to the winemaker or to the table grape producer. But the main question is, generating an optimum light environment in the fruit zone during and previous to ripening. Maximizing diffuse or indirect sunlight within the canopy interior should be key, and minimizing exposure of clusters to direct sunlight, particularly in warm climates, need to be adhered to. So this is another Syrah vineyard in southern San Joaquin Valley. The rows are 11 feet. Vines are spaced 7 feet apart. When I got called into this vineyard, they're like, what the heck is going on? I'm like, quit irrigating so much. You couldn't even drive a tractor through this vineyard. So they were having problems, attaining, even 16 degrees Brix in this, very, very, vigorous site. But needless to say, Rhonda Smith and Larry talked about this. Grapevine canopies are essentially, these solar panels that have these little gaps in them. So this vineyard is, planted north-south. It's a Scott Henry canopy. I do not recommend, you do this in California. It's too expensive. But, for demonstration purposes, the cereal box on its side, receives sunlight on this plane bound by FEHNG in the morning. And then it'll receive sunlight on its top, and then it'll receive sunlight on the westerly side of the canopy as well. We also receive some sunlight reflecting back into the canopy from the vineyard soil. And Johan Martinez measured a lot of this, reflection of this indirect sunlight back into the canopies in our experiments in Oakville and the north coast of California. We find it to be somewhat negligible that we do not put into our models anymore. But needless to say, this radiation effect has a beneficial effect on the whole canopy. One of my colleagues always jokes with me that I'm always measuring whole canopy photosynthesis in comparison to a single leaf photosynthesis. But in this case, the x-axis is the amount of sunlight falling onto the vineyard. The y-axis is net canopy photosynthesis, net carbon dioxide assimilated per vine. This increases very rapidly, and then it flattens out at a certain point in time, roughly about 1,500 sunlight units. The canopies are working. I mean, you can throw so much light onto them, but after a certain point in time, they do not start assimilating this essential sunlight into the system. The vineyard systems, you have leaf layers that make up the canopy. So as we measured these, when we tried to replicate some of the work that was done in New Zealand, we're assuming 100% of the sunlight is falling onto the Earth's surface. And as it hits the first layer of leaves, about 6% of it is reflected. We are seeing roughly about 10% of this 100% incident sunlight being transmitted into the secondary leaf layer, and 1% of this transmitted. And after about a third leaf layer, light is essentially extinct in these canopies. So, mm-hmm. No, it's reflecting back from the leaf, from the canopy back into the atmosphere. So why do we have to have canopies? If I talk to a lot of the consultants, as I'm meeting a lot of people on the North Coast, most of the consultants do not even consider having canopies on the grapevine to be essential. But the role of the canopies is to fix carbon, and the reason that we fix carbon is to make sugar. So we have the shoot system of the grapevine. Collectively, these will make up the canopy. As we are receiving sunlight, supplying water through the root system, the leaves are acting as a source, fixing carbon, giving out oxygen, and the fruit is acting like a sink, putting the sugar back into the berries. So we ran these experiments with Johan for a couple of years now. We left more leaves. We took off less leaves. So we rediscovered the wheel, meaning that we are able to change the ripening speed in bricks per day as we retain more leaves on these systems at different canopy densities. You have seen some of these slides earlier, but I want to re-emphasize again, exposure to solar radiation is not necessary to reach maximum skin anthocyanins in the grapevine species. As canopy porosity increases, you are going to degrade anthocyanins. We go through a lot of natural disasters in the North Coast, so we had to evacuate our lab in 2017, I think. So we had these green berries that we put on petri dishes on campus, and I added sucrose to the solution, complete darkness, so we can do an extension, I guess. But as soon as we start hitting 12% total soluble solids in this petri dish solution, we start coloring up these grapes. And this became even more evident when we were looking at these canopy structures, how they were fixing sugar. In the presence of red blotch with 110 rootstock or 420 rootstocks with two different hydric properties, there's a mechanistic relationship between total soluble solids and anthocyanins, milligrams per berry. You can see that as phloem transport is impeded with the presence of a virus, you are not making as much sugars, therefore you're not making as much anthocyanins. In the absence of red blotch virus or leaf roll virus, you're going to make sugars to a known amount, and then get your anthocyanins in this case as well. The role of canopies is also for regulation. They also help in the synthesis of abscisic acid precursors. Ashraf Al-Karimi talked about the role of abscisic acid in ripening. But in this trial, the plants were grown with irrigation withholding with a certain amount of deficit, or they were defoliated after a certain point of time in the season. The abscisic acid content kept increasing with irrigation withholding. But as soon as these vines were defoliated, abscisic acid production or content declined to half of what it was with just irrigation withholding. The photoassimilates travel within the plant, right? They're made in the leaves, and then they will travel down the plant, and they'll be translocated to different portions. So this is one of the key papers, and I've been a student for a long time before I graduated, I guess for about 7 years. So I read this paper in the first year of my PhD. I'm like, this was like in 2002. I'm like, and this is like brilliant. How come no one ever did this before? But then I realized the copyright date, 1989. So in this case, the authors mechanically removed a portion of the phloem by girdling, which is something my father did as a raisin grower, and then table grape growers still do this. But you can see how the photoassimilates are manipulated with the addition of mechanical impediment to the phloem. So you can put more photoassimilates, grams per carbohydrate per vine, to the clusters, to the leaves, and then reduce them in the roots. So you can manipulate the assimilation of these carbohydrate in these systems by impeding the flow in these systems. But we do not do a whole lot of girdling in wine grapes. There are some metaphysical things that are mentioned in the industry, such as you can rejuvenate red blotch positive grapevines by girdling. Yeah, you can rejuvenate them and start accumulating a lot of sugars earlier by girdling these plants. However, the purpose of girdling is to put a lot of carbohydrates into these berries, so you just end up with these like giant berries with dihydroxylated anthocyanins in this case. So you might have a chance to see that this afternoon at the Oakville station. So how we manipulate carbohydrate assimilation in grapevines is by manipulating leaf area to fruit ratio. And these are interchangeable. So we talked a little bit about the crop load index, Louis Ravaz's index. These two can be interchangeable because they're inherently related to each other. One of my predecessors, viticulture specialist, wrote this keystone paper, Dr. Dekuzlian with his major advisor. They summarize some of the data from this vine spacing and rootstock trial at the Oakville station. They looked at two rootstocks, 03916, which can be a very vigorous rootstock, and 110R, 03916. People use it for sites that have a lot of fan leaf, and Oakville is like a petri dish. Every disease known to mankind is there, I guess. So in this case, they regressed leaf area to a crop weight ratio, to a crop weight to a pruning weight ratio, and they got a very linear relationship. And then they assigned some points here where vines can be assumed to be undercropped or overcropped. And they decided on this by regressing this to the total soluble solids that can be accumulated in the berries at a known harvest point in this case. So x-axis here is leaf area to crop weight ratio. Y-axis total soluble solids. Again, you have this nice regression fit here, and then this system is optimized right around like 23 bricks, and then 0.65 square meters of leaf area per unit of fruit, or 10 Ravaz index, or a 5 Ravaz index. And if you're out of these windows, you're assumed to be undercropped or overcropped. When we talk about mechanized systems, we'll examine this again. So as you're managing canopies or crop loads, the yields in a wine grape. This is not uncommon. My lab is within the Tokalan district. I see this every year. The last 4 years I have been here. So the question always is, how much fruit do I drop? Do I even need to drop fruit? But of course, if you show up at a winery and say you're doing it all wrong, drop less fruit. Yeah, it's easy for me to say because I don't do this to make wine or make money. But dropping less fruit, the decision to do this is not so simple. So we have essentially to simplify two economic models, and there's an apparent trade-off between yields and quality. I mean, let's not fool ourselves. We sometimes can use yield as a multiplier of revenue, or quality as a multiplier of revenue. So for sake of discussion, I summarized these from the Grape Crush report. These are approximate data. District X grows 1.3 million tons on 77,000 acres. Average yield is about 16 tons to the acre. Growers are getting about $300 a ton. You're generating about $5,000 an acre of gross income. District Y, makes only 140,000 tons. Average, gross return is $5,000 a ton on 3.1 tons to the acre. And the growers then, in this case, is making $15,300 gross income to the acre. So, I mean, these are, known numbers, and, there's an apparent trade-off between yields and quality because the consumer votes with their wallet. Wine grape quality is an extremely complex topic. It's subjective, right? It's gradually changing. We have this, wonderful lab in Oakville. We can monitor everything, from a gene expression to all these, secondary metabolites. But aspects not related to grape quality is what determines wine price. It's the market niche and how much is invested in winemaking. But in the end, nobody likes sour grapes because quality of the vintages are related to mean sugar accumulation. This is from the Bordeaux vintage quality, and it's also related to the growing season mean temperature. So Johan showed this figure yesterday, roughly around 17 degrees Celsius mean season temperature seems to be the winning combination. And in our case, if you were to compare Bordeaux to Napa to vintage quality, again 18 degrees Celsius seems to be the sweet spot, roughly about 64 degrees Fahrenheit to get our vintage quality to where we need to be. However, the planet is getting warmer, so are viticultural regions, and worst vintages ever are related to accumulation of less than desirable growing degree days in known high-quality regions. So I'm asked this question every season. I go around the state giving a lot of talks, especially on the North Coast. How much leaf area do I need, and how many clusters do I need per plant? So I put everybody in the conference room at the Oakville station. It's not a very big place. I'm like, describe me the ideal canopy as a winemaker or a consultant that you'd like to see. And they said like, well, you should be able to throw a cat through this canopy. I'm like, wow, okay. So we set up this trial. So these are vertically shoot positioned trellises. We pruned it and adjusted to 22 shoots per vine, and there are 3 plants per treatment replicate. So on these shoots, we kept either 33% of the leaves, 66% of the leaves, or we kept 100% of the leaves. We kept 33% of the fruit, 66% of the fruit, or 100% of the fruit. So roughly about 45 clusters per plant, unheard of in Tokalon. So if you want to know what a plant looks like, if you can throw a cat through it, this is what it looks like. So it looks pretty bare. So this is 33% of the fruit with 33% of the leaves. And this is, at a treatment application, 100% of the fruit and 100% of the leaves with only the laterals removed. So, of course, for some reason, university planted these vineyards in the most damaging, sunlight interception, northeast, southwest. So we end up putting these mini skirts on them with these shade cloths to, help them not die. And then here's the treatment application when the canopies are mature. So they grew up to about 120 centimeters to 140 centimeters. So the canopies are healthy. They were irrigated at 65% of crop evapotranspiration replacement the whole season. So they were quite happy. The findings are not, surprising to us, but it was surprising to funding agencies and to our growers. Leaf area determines carbon fixation, not fruit. So this is net photosynthesis. I'm only showing you the most extreme treatments: 100% of the leaves, 100% of the fruit, 33% of the leaves, 100% of the fruit, and the other extremes. So here's what it looks like. If the vines are, for lack of a better term, in balance, and in our case, in Oakville, it's 100% of the leaves, 100% of the fruit, but in most cases, it's the leaves that's driving this. They're happy, they're not under stress, they're not overworking. If we do not have enough leaves, the plants are carbon starved, and they're working like overtime, constantly, and consistently. Net carbon assimilation by the smaller plants was high. So when I separate these out to extreme defoliation, extreme crop removal, whatever, amount of crop load has no effect on carbon fixation in the grapevine. It's the amount of leaves that you keep on these vines. So for lack of a better term, let's call this plant water status. This is stomatal conductance. Again, leaf area in this case determined plant water status, not the amount of fruit. Again, this wasn't surprising to us because we've known this. Leaf area is what determines plant water status, not the fruit you have. In this case, again, the undercrop plants, the extremely defoliated plants, were in overdrive consistently throughout the season. They were trying to open these stomates to exchange as much gas as possible and conduct water because they're feeling like they're carbon starved to the system that they have. I thought people were going to kill me. Because we have 1, 2, 3, 4, 5, 6, 7 time points in the season where we dug up 36 plants from this vineyard and then measured a lot of carbohydrates. So I'm just showing root starch here. And when you dig up, grapevines, they look like shallow graves. So I was afraid that they were going to push me in there, and then I wouldn't be able to come out. But the interesting thing that we found here is that leaf area determines the plant reserves, not the fruit. So these are mature producing vines. We let the vines adjust the first year, and then collected data in the first, second, and third. So now we're going into the fourth year of this trial. So when we do the treatment application, you can see the root reserves decline very fast. And the 33% leaves 100% fruit, 33% leaves 33% fruit. The vines that are in somewhat of a balance, they're hanging out pretty. They're able to push starch into the roots to store some reserves to push the growth in the next year. Again, leaf area determined plant reserves, not the amount of fruit we retained on the vines. So they drop and then they slowly catch up. But our saving grace in California is that we never really have a winter. So these, even with like the puny leaf area we have on these vines catch up, but they're 9 weeks behind. When you extremely defoliate them, it'll take them 9 weeks to catch up, to accumulate enough root starch. Again, not surprising to us, leaf area determines the speed of ripening, not the amount of fruit you have on the vine. Again, I'm just putting the extreme treatments here. The amount of fruit has somewhat of an effect, but I'll go into this a little bit later. The leaf area determines how fast these ripen. 100% of leaves, 100% fruit, 100% of leaves, 33% of fruit. They advance ripening by about 6 weeks. Is that something we want? I don't know. 33% of leaves, 33% of fruit, compared to 100% leaves, 100% fruit. They were, in fact, 9 weeks behind to reach 24 bricks in Oakville. And Oakville is a warm region. So going back into this, time to reach a desired bricks is then going to be determined by the leaf area to fruit ratio. So here's leaf area to total soluble solids and yield per vine to total soluble solids. Not much of a strong relationship here, in fact none. But when I derive the relationship between leaf area to fruit ratio, I get the linear relationship to hit a desired bricks. And desired bricks is a moving target in this market economy now, because we have some people that do not even consider harvesting grapes till about 27 bricks. And these, of course, will require much, much larger leaf areas at a known time. Here I'm showing the self-adjustment of yields due to carbon starvation. These are 2 different years. Main thing I want to show you is smaller canopies will lead to lower yields. One of our retired professors did a similar work, and it was published in 2006. He kept saying we cannot get vines with a crop load ratio of greater than 8 in Oakville. And that's not by, that did not surprise us when we reviewed that paper. We have a lot of self-adjustments of yields due to carbon starvation. When you take these systems and try to impose these extreme treatments, the vines have quite a bit of time to adjust because they have been source limited for so long. These figures here are yield per plant. This is 100% of leaves, 100% of fruit, declining color hue. As we drop the amount of fruit and the amount of leaves, I'm getting about 1.7 kilos, roughly about 2 pounds of yield per plant, which is something that these winemakers told us to achieve. But these are carbon starved, and this continues on year after year, and this is the number of clusters per plant, and of course, these are linearly related to each other, but this self-adjustment of yields is due to more carbon starvation than our manipulation in this case, because berry size was determined by the leaf area, not the fruit removal that we did. Here's the kinetic development of berry size. You see that the 100% of leaves, 100% of fruit had the greatest berry mass or berry weight, if we decide to put this into a hort technology. But 33% leaves, 100% of fruit, 33% leaves, 33% of fruit. The percentage of leaves that we retain on the vine is what determines berry size, not the fruit load that you have. Berry size is determined by our leaf area, not fruit, because we have an autocorrelation in this data. Yield per vine, when I plotted on our berry fresh mass, this is autocorrelated, but our leaf area to our berry fresh mass gives us a better fit in this case. When I drive the relationship between our leaf area to fruit ratio, I don't have that much of a great relationship in this case. So that got us to thinking. I've been doing a lot of mechanical management studies up and down California. Like, you cite one paper like, oh, mechanical pruning, makes smaller berries, more, surface to volume ratio, so on and so forth. And this is more so related to a sync competition than we previously determined. And you'll see this plot at Oakville this afternoon. This is a 5,000 square meter plot. That's spaced 1.5 meters by 2 meters, 1,341 plants to the acre. And this plot consistently yields 13.1 tons to the acre in Oakville. So I'm not trying to get kicked out of Napa and move back to Fresno, but that's the capacity of this site at ideal crop load. Yield comparison between vintages. Is it a reliable yardstick to write contracts on or demand from the vineyard owner? 2017 yields, 2018 yields. Yield kilogram per plant was roughly around 4, roughly about 10 pounds. In the second year, it's almost 1.5 times higher, 7 kilos per plant, roughly 17 pounds per plant. But of course, yield per plant or tons per acre year over year due to vintage differences is not really a reliable yardstick in our opinion. However, leaf area to a fruit ratio, or Rabas index, is a reliable yardstick. So here are the thresholds, undercropped, overcropped. We are able to hit, very good, ratios, or replicate the situation in California up and down the state of California. So this work with 100% fruit, 100% leaves, 33% fruit, 33% leaves. This relates to all the production situations that we have in California, because we might be able to hit 13 to 14 Rabas index in southern Kern County, but we're able to replicate these here as well. So I would not get too bound on the yields per plant that are in this trial. The speed of ripening is quite an interesting case. Here's 100% of leaves, 66% of the leaves, 33% of the leaves. Comparison of 2 years. We're able to see these relationships year on year. They are separated a little bit better in the 2018. But I want to point out that this is also going to be limited by carbon starvation in this case. And now the kicker. Cluster or berry thinning does not improve anthocyanin content in Cabernet Sauvignon and Oakville. So here's some untreated vines, because I like doing extra work. when I say I'm a fat guy. Other people do the work. I just like yell at them, I guess. So here's an untreated, commercially, managed, border plants that we also replicated and randomized in the study. Here's 100% of the leaves, 66% of the leaves, 33% of the leaves. 100% fruit, 66% of the fruit, 33% of the fruit, linear decline, linear decline, linear decline. The interesting thing here is that as I reduce the number of leaves, I get a little bit of a bump in anthocyanin content, but this is consistent over years. If I retain less crop on these vertically shoot positioned canopies, I'm going to end up with less anthocyanins. Let me ask you the question: why? I don't want to answer the question now, but why? Let me answer the question. 33% of the fruit is going to be exposed much longer, about 9 weeks longer. So they're hanging in this like 110 degree heat, 100 degree heat in September, much longer. And it's just being degraded. To start off with, they did not have enough bricks accumulated in the berries, and henceforth, the mechanistic relationship between anthocyanins and sugar was, off balance to start out with. This is total flavonols per berry. So Johan presented this. These are, solar receptors in the berry skin. So we did not have that great of a relationship here. Since these VSP canopies are, ideally, designed to, intercept or expose the berries to a total amount of radiation. So they're not, separating that much. We have a little bit of a difference in the berry skin flavonols in this case. Here's the effect of skin proanthocyanin content. So this is biosynthesis. 100% of leaves, 66% of leaves, 33% of the leaves. Skin tannin content will increase as I, retain a little bit of as I retain less berries, but it will decline as I retain less leaf area on the vine. So this is skin. So the total content may be related to the mean degree of polymerization of the berry proanthocyanins or tannins so we can interpret it as a proxy to astringency of these berries. So when I put the tannin content with the seed and skin proanthocyanidins, leaf removal decreases, fruit removal increases tannin content. So we've been doing these degradation studies in Oakville to see if this warming climate is going to affect our signature tannin mouthfeel in this case. We can degrade the or remove the astringency and bitterness from the berries by removing a little bit of the leaves, and we can manipulate it more reliably by removing a little bit of the clusters in this case. So we found somewhat of a reliable relationship, at least to manipulate a mean degree of polymerization in the tannins with fruit thinning. But this can also be handled in the cellar more reliably, is what I'm told. But I'm not a winemaker. So in the end, everybody's paying a lot of money to do this crop load control consulting. But there are more important things as viticulturists can do on their own in the vineyard. Canopy size and shape. This is what determines photosynthesis and sugar-induced growth. Plant-reduced carbon pool. This is what manipulates berry enlargement and sugar allocation into the grape berry. And this is what determines berry size. Canopy size and shape will also determine abscisic acid precursors, because if you remove too many leaves, you're not going to increase your abscisic acid content as reliably as you can with water deficits. So abscisic acid precursors, as you manipulate berry size, the dilution of soluble salts and osmotic potential is what will get your ripening or soluble salts accumulation affected. Only then water deficits and somewhat of a crop control will start affecting other ripe grape berry traits, mainly proanthocyanidins. So this project is going on for another year. So we got the question yesterday, are you looking at green flavors? Unless you're purposely promoting green flavors like we would in San Joaquin Valley by generating these giant canopies, or as some of my predecessors did with shading these Cabernet berries with black cloth, we do not see that big of an odor-active relationship between methoxypyrazines and crop load control in north coast of California. See Mike standing up. The main take-home messages: berry size and yield are more sensitive to canopy size, more so than crop load or irrigation is what we found in Oakville. But we're irrigating 0.3 acre feet the whole season, so it's not that big of an irrigation amount. Small canopies are more likely reducing plant reserves. In our case, we quantified root starch for this extension talk. Challenge for increasing yields is what we're finding out is that controlling big canopies early in the season. So if you can control canopies early in the season, we received almost a meter of rain already this year. So controlling these canopies early in the season, will be a challenge in North Coast. My perspective is still, climate is changing. We have increased annual accumulated growing degree days over the past 5 decades, more frequent than intense heat spikes. Light solar radiation is not limiting. Damage occurs at a very low light exposure, greater than 20% of the light intercepted in the fruit zone. So I'm citing 1, 2, 3, 4, 5 papers within the last decade that has found the exact same thing. Do not overexpose, do not over-remove leaves in this case. And we're also finding out that greater applied water amounts are not relieving the stress from this excess solar radiation that we might be putting on these berries. We talked a little bit about the shade nets yesterday. We're creating these situations ourselves. They can be used to decrease incidence of solar radiation in the fruit zones. And I'll stop here. We'll take a break, I guess, and then I will continue. Raul? I'm not looking at it myself. I'm looking at it with a bunch of people. But yes, we're looking at it. We're tracking it. So these trials were done. So that's why it's called research, I guess. So, but we have a mechanistic design, and we can apply a lot more advanced techniques to look at fruit chemistry, like some of the gene expression, so on and so forth, to train more people. A lot of this stuff was done, but yes, we're looking at them individually. So uprooting vines, is a lot of work. You have to do with a backhoe, like shovel work. But analyzing these, takes a long time. So 7 time points within the season is horrible. The trial has another portion. The middle plants also got a stable isotope nitrogen, N15, on both species. It was applied as ammonium nitrate. So we're looking at the partitioning of the nitrogen within the system, because we can still see that nitrogen in the must. Wines were made from this by Cameron and Mary at Groth. The wine is made. It's being analyzed now at Oakville campus, and we'll see. If what we're seeing in the Bay Area holds true. You don't need very sophisticated equipment. When you put it in the wine glass, you can tell if something is washed out or intensely colored. Yes.
So am I understanding correctly that you're also seeing a direct and positive relationship between leaf area and the amount of carbs stored in the trunk and the roots for the following year?
Yes, that's correct. That's correct. The question was are you seeing a direct relationship between increased leaf area and stored carbohydrates in the permanent parts of the plant? Yeah.
But the shaded leaves are not providing anything. In fact, they're drawing from, correct? So it's not necessarily the more leaves you have, the more leaf area.
Yeah. The question is, are the shaded leaves acting as a drain on the system? These canopies have 100% exposed leaf area. The canopies are a mini lyre. The cordon wire is here. If you place them at a 45-degree row angle or a 135-degree row angle, both sides of the canopy get somewhat of the light equally distributed. But the important thing in these UCD 30 or 60 trellises is that the middle of the canopies are getting a lot of sunlight as well. So if we put these canopies at a 22-degree row orientation from true north, it would be the ideal row orientation. Because if we put them northeast to southwest, we heat up the afternoon side a lot more than than this somewhat uniformly distributed heat distribution. But we know how much photosynthesis each leaf is doing in these canopies. So in these new canopies, there's no unexposed leaves. It's kind of an unfortunate thing, but it is what it is.
So that's different from the other study that you cited where you said 10% sunlight.
20%.
10% radiated to the second leaf layer and 1% radiated to the third.
Yes, those were from traditional sprawling canopies.
And these are not. These are still sprawling.
Yeah, no, this is still a sprawling system because as the shoots grow out of the top, they'll sprawl to the side, so they will provide some relief from the size of the sun.
So it's mainly the 133 orientation that causes this to get more sunlight in the second and third leaf layers?
You can say that. So, anyways, let's take a break. Sure.
When we were talking about the cluster trials, the cluster digging trials, at what point did you say in the cycle when was the cluster digging happening?
Yeah, very good question. The question is, at what point were the clusters removed from the plant? So there are various schools of thought. You can remove fluorescence before bloom, or you can remove infrutescence, or you can do the green drop after veraison. So in our experience, post veraison, cluster drop is not effective at all. So the clusters here were thinned right after set. So the clusters had set. I didn't show the data here, but due to carbon starvation, even though we removed the clusters after set and applied the leaf treatments after set, we still dropped berries from the already formed cluster due to carbon starvation. I mean, in our experience, if you're going to do a cluster removal, some cluster removal will be needed in the form of secondaries. You probably are going to have the best effect when the berries are about 3 to 5 millimeter stage, around a BB size. One of my predecessors always was against cluster removal. Just wait for the vines to ripen. they do not really ripen if you do not have the correct leaf area. They just dehydrate. So having the correct leaf area is key, in my opinion.